students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as alkenes. Let's see this. Alkenes. Now what do we understand by alkenes? Alkenes are unsaturated aliphatic hydrocarbons containing carbon-carbon double bonds. Alkenes are unsaturated aliphatic hydrocarbons containing carbon-carbon double bond, right? Now, since they also form oily products on reacting with halogens, they are called as olefins, that is oil forming. Since they form oily products on reacting with halogens, they are called as olefins. They are called as olefins, that is oil forming. They have general formulas CnH2n. Is CnH2n. That's the general formula of alkenes, right? They contain two hydrogen atoms less than the corresponding alkanes. They contain two hydrogen atoms less than the corresponding alkanes. Right? Next, what else can I say about them? The double bond in alkenes is also called as ethylenic or olefinic bonds. Alkenes are more reactive than alkane due to the presence of double bond. Alkenes are more reactive than alkanes due to the presence of carbon-carbon double bond. Fine. Next, let's see the nomenclature, guys. Now, while doing nomenclature, let's see on the right hand side. We just revise our basic. When you have one carbon atom, that is METH. 2 carbon atom is ETH. 3 carbon atom is prop. 4 carbon atom is but. 5 carbon atom is pen. Remember, all you need to do is count the number of carbon atoms. You have to make sure that you count your carbon atoms correctly. Right? Now, let's see the nomenclature, guys. Nomenclature. Right? Formula. Common name, IUPAC name. Common name, IUPAC name. Now, H2CCH2, right? How many carbon atoms, guys? Count the number of carbon atoms. There are 2 carbon atoms, therefore this is going to be ETH. Common name for, there's a double bond, right? For common name of alkenes, it is YLENE. So this is going to be ethylene, double bond, therefore YLENE, right? The IUPAC name, 2 carbon atom ETH. For IUPAC name, if there is a double bond, you put ENE. So this is ethene. So common name is ethylene and IUPAC name is ethene. Fine. Next, let us see another one. H3C CH2. Count the number of carbon atoms. How many carbon atoms? 3. 3 carbon atoms, that means prop. 3 carbon atoms, that means prop. right? Common name, there's a double bond here, so YLENE, so this will be propylene, right? 3 carbon atom, therefore prop. IUPAC name, therefore ENE, right? Next, CH3C, CH3, CH2, right? Now, 1, 2, 3, 4. 4 carbon atoms. Since there are 4 carbon atoms, therefore this is going to be BUTY. Double bond, therefore LENE. I have a methyl group in the branch. Since there is a methyl group in the branch, therefore this will be iso. So this will be isobutylene. Fine, do we get this thing clear? Now, IUPAC name. While doing IUPAC name, you have to first find out the primary chain. Primary chain is that chain that contains maximum carbon atom. The straight chain is the primary chain, right? The straight chain has 3 carbon atoms. 3 carbon atoms, therefore prop. Double bond, therefore ENE. Double bond is connected to the first carbon atom, therefore 1 propene. Now this is first carbon atom, this is second carbon atom. The methyl group is attached to the second carbon atom, therefore this is 2 methyl 1 propene. Fine, do we get this thing here? So the IUPAC name will be 2 methyl 1 propene. Next, let's see another compound. CH3, CH2, CH2, sorry, CH and CH2. Count the number of carbon atoms. 4 carbon atom, therefore but. Double bond, therefore YLENE. Right? Now, the IUPAC name, 4 carbon atom, therefore but. Double bond, therefore ENE. Double bond is attached to the first carbon atom, therefore 1 butene. Right? Next, CH3, CH, CH, CH3. Right? Now, this here, let's see this. You have 4 carbon atoms, therefore but. Double bond, therefore ENE. Double bond is attached to the second carbon atom. Since double bond is attached to the second carbon atom, this is sec-butylene. Right? 4 carbon atoms, therefore but. Double bond, therefore ENE. Double bond is attached to the second carbon atom, therefore 2-butene. Fine, do we get this thing clear? So that was my nomenclature. Next, let's see the structural formula and the electronic structure. First let's see the structural formula. Now, when I look at the structural formula, I can say that suppose if I consider the structural formula of, say, ethene. Ethene means there is going to be 2 carbon atoms. ENE, that means double bond. Now we know that the valency of carbon is 4. Valency of carbon is 4. That means 2 hydrogens here, 2 hydrogen here. That's going to be my structural formula, right? The electronic structure. This was my structural formula. Right? Same if I see the electronic structure for this. Electronic structure. Carbon-carbon. Right? Now I'm going to show the electrons of carbon by crosses. So this carbon has 2 electrons and 2 electrons. Both the carbon share a pair of electrons and form the bond here. Now, valency of carbon is 4, right? So 3 and say this is the 4th carbon atom. You share with a hydrogen, you share with a hydrogen, hydrogen, hydrogen. So this is going to be my electronic structure of ethene, right? This is your electronic structure. Okay, once we have this, next let's see what we will see is isomerism. Right? What do we understand by isomerism? A phenomena by which a compound can have same molecular formula, two or more compounds can have same molecular formula, but different structural formula is called as isomerism. Right? A phenomena in which two or more compounds have same molecular formula but different structural formula is called isomerism. That is what is isomerism. Now, so that means here they will have same formula but different structural formula, same molecular formula but different structural formula. So what are the different types of isomerism? The types of isomerism exhibited by alkene are chain isomerism, second, position isomerism, and third is geometrical isomerism. So these are the three different types of isomerisms that are exhibited by alkene. Now let us try to understand each one of them in detail. First, let us understand what is chain isomerism. Right? What is chain isomerism? The isomerism exhibited by a compound due to the difference in the nature of the carbon chain is called as chain isomerism. I'll show you this with the help of an example. Let me write the definition first. Isomerism exhibited by the compound due to the difference in the nature of due to the difference in the nature of carbon chain is called chain isomerism. Right? Now what does this actually mean? Let's see. Let's consider example butene. Let's take the example of butene. Now butene, I can have a straight chain for butene. I can have straight chain, that is I can have butene, 4 carbon atoms, butene double bond, so H3 valency, H2, H, H2. Right, this is straight chain, or I could have a branched chain. Branched chain as in I can have CHC, CC, and I can have one carbon in the branch. I could have a double bond here. So valency is 4, so 3. Valency is satisfied, 3, 2. This is also butene, but here this is in a branch. So the first one is 1 butene and the second is 2 methyl 1 propene. They are isomers of each other, and this kind of isomerism is called as chain isomerism. It is exhibited due to the difference in the nature of the carbon chain. Because the carbon atom has been brought into the branch, therefore you have isomerism here. Fine, do we get this thing here? So that is called as chain isomerism. Butene and 2 methyl 1 propene, both are same. Okay. Next, let's see the next thing. Let's consider position isomerism. What is position isomerism? Now, isomerism exhibited due to the difference in the position of double bond. Isomerism exhibited due to the difference in the position of double bond in the same type of carbon chain is called as is called as position isomerism. Right? For example, I could give you an example as I could have, if I consider the example, I can have butene, CH3, CH2, CH2. Here the double bond has been attached to the first carbon atom, or I can have, this is 1 butene, or I could have 2 butene, wherein I could have CH3, CH, CH, CH3. In both the cases, this is butene. Here, the double bond is attached to the first carbon atom. Sorry, this should be single bond. And here, the double bond is attached to the second carbon atom. So in one case, double bond is attached to the first carbon atom. In the other case, double bond is attached to the second carbon atom. This is called as position isomerism. Here, isomerism exists because of the difference in the position of the double bond in the same chain. So this is positional isomerism. The next you have is geometric isomerism. Geometrical isomerism. Now this isomerism is exhibited by the compound due to the difference. This is isomerism exhibited by the compound due to, it is an isomerism exhibited by the compound due to the difference in the special arrangement, due to the difference in the special arrangement, due to the difference in the special arrangement of groups about doubly bonded carbon atoms. Bonded carbon atoms, right? It is also called as CIS, trans isomerism, also known as CIS, trans isomerism. Fine. Next, now in this you have two types of isomers. One is called as the CIS isomer and the other is called as the trans isomer. I'll show you the difference between the two. Example, Let me show this to you with the help of an example. Suppose if I have a compound such as carbon-carbon double bond, CH3, CH3, H and H. Right? Now in this particular compound what we observe is that the similar groups, that is CH3, CH3 and N and H and H, lie on the opposite sides of the double bond. Such kind of an isomer is called as a trans isomer. So this is trans 2-butene. So what is a trans isomer? In which the similar group lie on the opposite side of the double bond. If the similar groups lie on the opposite side of double bond, then that is called as trans isomers. Right? Next, I could give you another example like carbon-carbon double bond, CH3, CH3, H and H. Here, what we observe is that in this case, you have similar groups which lie on the same side of the double bond. Both the CH3 are on the same side of the double bond and both the H's are on the same side of double bond. This is called as CIS structure. So CIS 2-butene. These are the two different types of geometrical isomerisms that you have. Next, let's see what are the different methods of preparation. Right? Amongst the methods of preparation, you have one is dehydration of alcohol. Right? Now, dehydration of alcohols. What do you mean by dehydration of alcohol? Dehydration means elimination of water molecule. Right? Now, so when alcohols are strongly dehydrated by a dehydrating agent like concentrated sulfuric acid, they lose a water molecule and get converted into alkene. See, I'll show you this with the help of an example. What happens when ethyl alcohol is heated with 95% sulfuric acid? Ethyl alcohol with 95% sulfuric acid. Right? Let's see this. Ethyl alcohol. Now, ethyl. Ethyl means 2 carbon atom. Ethyl, so single bond. Alcohol is OH. Now we know that valency of carbon is 4. This is single bond, that means this will be H3. This is going to be H2. So CH3, CH2, OH is my ethyl alcohol, is heated with 95% concentrated sulfuric acid, right, at 443 Kelvin. Instead of 95% sulfuric acid, you could have also used aluminium oxide as the catalyst, but in that case, then the temperature would have been 623 Kelvin, right? Now dehydration would take place, that means it would lose a water molecule. Water molecule comes out, H2O comes out, that means one H comes out from here, one H comes out from here and one O is out. So that will leave you with H2C, CH2. To balance this, this has to be double bond. So here you have ethyl alcohol getting converted into ethene, right? That's how your ethyl alcohol gets converted into ethene. Let's see another example of this kind, guys. What happens when propyl alcohol with 95% sulfuric acid, right? Propyl alcohol with 95% sulfuric acid. Propyl alcohol, right? Propyl means 3 carbon atoms, alcohol means OH, right? Propyl means 3 carbon atoms, alcohol means OH. Balance the reaction. 1 carbon atom, therefore 3 hydrogen, 2 bonds, therefore 2 hydrogen, 2 bonds, therefore 2 hydrogen. So that's why propyl alcohol is treated with 95% sulfuric acid at 443 Kelvin, right? In which case again you would have dehydration taking place. So water molecule comes out, right? Water molecule comes out means OH and one H is out, right? If one H is out, that will give me CH3 C double bond CH2. So 3 CH double bond CH2, right? This is propyl alcohol and this is propene. Fine. Now I could also do this with secondary alcohol. For example, if I say what would happen if sec butyl alcohol is treated with 75% sulfuric acid. Sec butyl alcohol with 75% sulfuric acid, right? Butyl alcohol means 4 carbon atoms. Butyl means 4 carbon atom. Sec butyl alcohol, that means alcohol is attached to the second carbon atom. Butyl means 4 carbon atom. Alcohol means OH. Sec butyl alcohol means OH is attached to the second carbon atom. Now do your bonding. H3 2 1 2 3 H H2. This is my sec butyl alcohol, reacts with 75% sulfuric acid. Sec butyl alcohol reacts with 75% sulfuric acid. You would have dehydration taking place. But the question here is, from where do I remove the hydrogen? I have to remove hydrogen for water. From where do I remove hydrogen? Right? In order to know from where hydrogen has to be removed, you have to apply something called as Sator's rule. Now Sator's rule says that in higher alcohols or higher alkyl halides, hydrogen atom from adjacent carbon atom carrying less number of hydrogen atoms is preferentially removed. That means I could either remove, here is my alcohol, that means OH is definitely being removed from here. Now either I could remove hydrogen from here, or I could remove hydrogen from here, right? So in that case you will have, from where do I remove hydrogen? This is going to be, first let me remove water molecule. This is, water molecule is out, right? That will leave me with CH3. Here your hydrogen is going to be removed from the compound adjacent to the compound carrying less number of hydrogens, right? So in that case this is going to be CH3 CH double bond CH CH3, right? So here, if how have I applied Sator's rule? I have applied Sator's rule by saying that hydrogen atom is removed from adjacent carbon atom carrying less number of hydrogen atoms, right? Do we get this thing clear? Right. Okay, we'll stop this here for the day. Thank you very much.